Hi, my name is Ruihe. I'm from Electrochemical Society and Engineering Group from Imperial College London. Here I would like to introduce my work about effect of solvent segregation on the performance of lithium-ion batteries. So this is my overview. I'm going to talk about how important lithium-ion battery is because you've already listened lots of talks about that. I will start from the electrolyte. So electrolyte is, of course, very important because it is the only component that in contact with all the other components inside the batteries, the cathode, the anode, the current collector, etc. And if we look at the electron, if we think about the electron energy level, the difference between the anode and cathode is so big, and the electrolyte must be compatible with both of them. So obviously it needs to have very wide range of window in terms of electrochemical potential, but even that it still needs to form some sort of SCI or CI to be fully compatible. The electrolyte also need to satisfy different requirements, such as to balance the conductivity, viscosity, thermal stability, and different solvent has different functions, especially what they're good at. So sometimes we need to combine 2 or 3 different solvent components together to make a balance, such as EC, EMC, DMC, and this is where solvent segregation happens. Lithium-ion is solvated by solvent molecules, but actually it will preferentially reclude those polar cyclic carbonate components, such as EC, relative to the nonpolar linear counterparts like DC, DMC, EMC, etc. Here is a microscopic mass spectroscopy evidence of that. And on the left, on the right, if we think about a journey of a solvated lithium from solution bowl to the graphite surface, of course it carries EC with it, but when it reached the graphite surface, it desolvated and intercalated into the graphite, and those EC were just left there. And because EC participate into the SCI reaction, so the other solvent, the fact that there were lots of EC on the particle surface will probably mean that it will also be preferentially join or participate into the SCI reaction. So how is solvent segregation can be seen in a microscopic point of view? So here what we show is a current puzzle experiment in a Hitov cell with EC, ENC blended solvent in LiPF6. It's done by Wang and co-authors. What they do is that they have a Hitov cell, and there are 3 chambers in it, the anodic, natural, and cathode, and they apply certain current for a period, and at some point they stop. They cut the valve into cut the Hitov cell into 2 parts, and by closing the wave in the middle, and upon equilibrium, they measure the solvent composition in the 2 chambers, and then what they find is that the EC component are more than EMC on the left hand side, and on the right hand side is the opposite. So this is microscopic evidence of solvent segregation happening due to cycling. So now we need to look back into the classical DFM model, or let's say P2D model. In this model, there was one assumption that has been overlooked, which is the single solvent assumption. It assumes the electrolyte contains only one salt, which further dissolve into anion and cation, and one background solvent. To describe this, we just need one transport equation and a mechanics equation. But now we have one more solvent, which we note as O here, and we select EC in our case. And now that we have one more solvent, we will need to add one more equation for it, as shown here. and also to consider the interactions between the different components, we will have a cross diffusion term here. And of course, we notice that the solvent polarization over potential, it will affect the current as well. So here what we show is the model input. With this table, I highlight the electrolyte property, which is quite a lot, and all the other parameters are the same from the two references which correspond to the LGN50 high energy cell. So there was one thing I want to highlight is that the co-solvent model, or let's say multi-species transport theoretical framework, has been there for years, and the de-solvates model still assumes single solvent mainly because the parameters are just too much if we increase only one species, as can be seen here. So thankfully, there was Professor Charles Morrow's group in Oxford has been doing lots of fundamental electrolyte characterization, and recently they have measured the liquid junction potential using a concentration shells as a function of both EC and lithium-ion concentration, which can be used as a very useful input as our model. And for all the other parameters, we still have to go into different literatures and find some parameters for each, find some values for each parameters. To implement this model, we use the open source modeling tool PyBan. It is originally developed by researchers in Oxford, Imperial, and many other researchers in other part of the world, and it is an actively developing tool, still keeping update, and our group has contributed quite significantly to the PyBan by adding different aging mechanisms. So we have people specialized in silicon related degradation, and myself focus more on electrolyte related degradation, and someone work on lithium plating and cathode degradation, and we are also trying to fully couple all these different mechanisms together and investigate the different complicated interplays between the different degradation mechanisms. And I also want to highlight that I also an active developed member of this team, and this is a very active community. If you raise a question in the discussion section in the on GitHub, you normally can give an answer quite quickly. With that implemented, here we look at the model validation at 2C Git. So the model is almost on top of the experiment, as can be seen here, and even if we zoom in a lot and see different puzzles, we still get quite decent fit. But a note I want to make here is that the single solvent, i.e. the classical de-solvates model, can also fit this equally well. So this is just to show that our double solvent model doesn't make a mess. Now that we have validated the model, we can see how it can predict. So first thing, we look at the concentration distribution during discharge. On the top is the double solvent model, and on the bottom is the single solvent, i.e. the classical de-solvates model. And obviously, we can capture the EC concentration profile, which is opposite to that of lithium-ion profile. And we can also see the different contributions that make the concentration profile looks like this, such as the source turn, the self-diffusion turn, the cross diffusion turn, and the migration turn of the two species. And as comparison, the classical de-solvates model obviously cannot capture such complicated concentration profile. Then what's the effects of such concentration profile? So now here we look at both the overpotential in electrolyte and the electrolyte transport properties. So with the double solvent model, we can predict more both lithium-ion polarization over potential and EC polarization over potential. And this is just because at a quite extreme case, the double solvents will have a little bit higher lithium concentration than the single case because the EC is dragging it. And for the EC, because the single solvent doesn't have EC concentration profile at all, so the polarization potential will just be 0, whereas if we have it, we can predict an extra 15 millivolt over potential, and that's quite significant to the batteries, especially if you consider when you need to do the SOC estimation, etc. And for the electrolyte properties, it does not make quite a big difference, but still there are some difference for the conductivity at the extreme case. And if we plot such effects in terms of at the end of discharge at different C rates, we can see how it changes as the C rate increase, the over potential increase, and that's because the concentration gradient increase. And if we summarize this in terms of effect on rate performance, we can see that the double solvent model predicts 6% more of power loss at quite high C rates compared with the single solvent model, and that can be ascribed to the difference in the either lithium polarization over potential and also EC polarization over potential. But what about the effect on the cycle life? So as we mentioned before, the EC concentration will affect the SCI reaction rate as it participates into the SCI reaction. So here we pick the interstitial diffusion limited SCI reaction, which is proposed by Volkov-Zimbers and co-authors, and it assumes the diffusion of interstitial lithium in the SCI is the rate limiting process of the SCI reaction. And we add here a linear dependency on the EC concentration, and the result is shown here. So the EC concentration profile looks like this. Its maximum and minimum point occurs at the current collector side. But for the surface potential difference on the negative electrode, it is lowest at the negative and separator side, or let's say tend to be more negative. As a combined result, normally the SCI current density would be highest at the negative separator side, but this is where the EC concentration gradient is the smallest. Whereas on the current collector side of the negative electrode, even though the EC concentration profile is linear, it's bigger, but it has only a linear dependency, and also the SCI current density is relatively smaller. So combining this together, the model predicts slightly more capacity loss in the long run. But I need to note that this is for our case only. For the parameters, for the cell parameters, and for the specific format of JSCI here. Now I want to make a summary on my work. I have added a little bit more physics compared to the classical DFM model, which is the double solvent transport. With that, I can capture not just the lithium-ion concentration, but also the EC concentration profile, which affect the electrolyte properties and polarization or potential, and also the SCI current density. And all these changes ultimately make a difference on the aging and rate performance of the cells. So this model predicts a solvent polarization or potential can be up to 50 millivolt during discharge, and that corresponds to 6% more capacity loss than the single solvent case. And it also predicts slightly more capacity loss compared with the single solvent case, using the interstitial diffusion limited SCI with a linear dependency on EC concentration. So, but I need to highlight that this is for a high energy cell with electrolyte properties from different literature. So in the future, it will be very interesting to see what this model can predict using a complete set of double solvent electrolyte properties. And how about high power cells, which is designed for high current rate, and how this would work during SCI formation, as during SCI formation the EC concentration may make an even bigger difference. And there are lots of molecule dynamic modelings showing that how the solvation structure of lithium can affect the performance on side reactions, and it will be interesting to see how this knowledge can be transferred to a continuum level with this model.